When we deal with ideal gas mixtures and we're interested in the change in entropy, we have to remember for ideal gases, internal energy is a function of temperature only, enthalpy is a function of temperature only, but entropy is a function of temperature and pressure. So if you were asked to calculate S2 minus S1, you would say, okay, it's going to be the mass times lowercase s2 minus s1, which the mass times s2 naught minus s1 naught minus r natural log of p2 over p1. Do you remember that type of equation? Where S naught is the entropy at low pressure, a function of temperature only. So we segment or separate, this is the function of temperature, contribution to the change in entropy, and this is how pressure or the pressure changes affect the entropy change. So if you had a mixture now, you would sum over each of the components of that change. Now the other thing what we want to do is we want to say constant specific heats. Otherwise you can still do it, but you just have to go into the tables and it's not as simple to write. So what I'm going to do is I'm going to write C sub p natural log of T2 over T1 minus R natural log of P2 over P1 for the component I, and then you sum them up over all the i's. True? Do you like that equation? Look good? So if you multiply and divide by the mass of the mixture, again that's the same definition as what we had, the sum of all mi's is the mass of the mixture, then you'll get the mass of the mixture times the sum of the mass fractions for each component times the same term. I don't know if I should rewrite it, but it's C sub p natural log blah blah blah. Okay? So you can see that it's a little bit of a challenge to compute it. Let me go ahead and write it out. C sub p natural log of T2 over T1 minus R natural log of P2 over P1. All right. Now this subscript I, you go in and investigate. Do we have a specific heat for each component? Let's say oxygen, methane, carbon dioxide, whatever the components are of that ideal gas mixture. There are different C sub p's, so we want the subscript I. But does it make sense to have T2I and T1I? Do we have partial temperatures? No, we don't have partial temperatures. So it's just one temperature is the temperature in equilibrium for all the components that are in that ideal gas mixture. Now we have minus R, but R was R bar divided by the molar mass, and each of them have different molar masses, so yes, it's R bar divided by M sub I. True? How about pressure? Can we talk about the partial pressure of component I at state 2 and the partial pressure of component I at state 1? You can. And so what you want to do here is you want to replace those partial pressures by yi times P2 and yi times P1. So the equation will become the mass of the mixture times the sum of the mass fractions for each component times the specific heat for that component times the natural log of T2 over T1 minus the universal gas constant divided by the molar mass for that component, the natural log, and this is where yi P2 divided by yi of P1 come into play. Now, in our gas mixtures, we're not going to have reactions. So the amount of CO2 stays the amount of CO2. The amount of methane stays the amount of methane. But when we get to the next chapter, when we have combustion, we're going to take oxygen and methane and turn it into CO2 and water vapor, right? That's combustion. And there you have to pay attention to changing Y's for each component. The amount of carbon dioxide before the combustion is low. After the combustion, the amount of carbon dioxide in the gas mixture is high. But at this point in this chapter, we can cancel those because we have non-reacting gas mixtures. We can also work it out on a molar basis. It looks very similar to this. Let me just say that you would have the number of moles of the mixture times the sum of the mole fractions times Cp bar I, natural log of T2 over T1, minus R bar, natural log. The yi's cancel, you're just left with P2 over P1. For how to calculate the change in entropy for an ideal gas mixture. All that look good? Ready to solve some problems?